Thank you, Ramon, for this very nice talk. So it's open for questions. Sarah, you're first.
Yeah, thank you for the interesting talk. So I'm not sure if I misunderstood you, but if I understood you correctly, at least in the first case, you assumed that you have a linear process before you could infer the directionality of your network because you mapped it to this autoregressive. But in principle, you would not need to assume a particular process to infer directionality, right? You can also get that from causal inference tools agnostic to a certain model. Is that too data intense, or why didn't you pursue this kind of route, which would be more general, I think?
So we considered using things like transfer entropy, like to just measure as a directedness kind of correlation measure.
Yeah, exactly.
One of the
That's
reasons
what I mean.
that would be one way to measure asymmetry. It's a bit more difficult in continuous data. So transfer entropy is designed for kind of discrete data, and it requires lots of choices about binning and things. But we really wanted to show the link between the irreversibility and the asymmetry. So we wanted a method that could basically do both. And with the OU process, we get both the asymmetry and the entropy production, because we can then measure it in a model-based
which is really
way.
nice. But at the same time, I think a linear dynamics is probably quite unrealistic if you think about neurons, right? They are like excitable systems, so they need to be very nonlinear, I guess.
So individual neurons are very nonlinear, and but these are macroscopic brain regions, and most models of macroscopic brain regions are nonlinear. But there's a recent paper, a Nature Biomedical Engineering paper from Danny Bass's lab, that shows that linear models outperform nonlinear models for large-scale brain imaging. That's probably because our nonlinear models are bad, not because the brain dynamics are truly linear, but it's a first approximation.
Okay, thank you.
Okay, Patrick?
Hi, thank you very much for this talk. So I guess the measure for entropy is this kind of looking at the time antisymmetric part of activity, but it could also just be, because it's not related to heat here, it could also just be related to a general burst of activity, and that is just one aspect of that activity, that the entropy production is going up. So did you also look at some kind of time symmetric quantifier of activity? Makes sense?
Not exactly. If you could clarify a bit more, what do you mean by time symmetric?
I mean, you could just look whether you have lots of state changes happening in a certain unit of time. Is that correlated with the increase of entropy production, or is it kind of maybe even anti-correlated?
That's not something that I looked at with this continuous model. That sounds like something that would be like quite easy to do with if you're using a discrete state process. So if you're using an HMM or a low number of states Markov model for brain dynamics, like in the original paper, they just clustered it into 8 states. But it's not something that I looked into.
Okay, thanks.
Okay, are there any further questions? Okay, then I have a naive one to the very beginning. I mean, you associated directedness with different rates when you had this Markov model, right? When the forward and the backward rate are very different, you said it's more directed. And you said that this would be related to a higher entropy production. But I can easily imagine Markov networks where the rates are very unequal and still there is no entropy production at all.
So in the processes that we used, they are it's a kind of a necessary and sufficient condition. So in the Ising model, if the connections are symmetric, it's in detail balance, and the same with the OU process. It's not always true for the random walk. That's true. For example, you can take just that's the reason with the two node example that I had, we didn't have the random walk results because it's in detail balance. So it is true. That's one of the reasons why we used different measures of directedness, which I didn't have time to go into. But there are some kind of local measures where you have like say a cycle graph, which can be in detail balance. But they're under some measures of directedness that is very directed because it's a cycle. And so each edge only runs one direction. Under other measures of directedness, so spectral measures, that is undirected, right? So it's got no hierarchy whatsoever. Those adjacency matrices would be normal. And so that's one of the reasons why we used 4 different measures of asymmetry. And there are some other results that I didn't include because it's a 10-minute talk, but we were interested in how different kinds of directedness drove entropy production, because there's not just one notion here.
Okay, so thanks, Ramon. We are perfect in time.
Thank you.
And so please stop sharing. And the next one will be Janik Schüttler from Cambridge.
Yeah,
Janik,
hi everyone. Yeah, let me just share the
yes, we
screen.
can hear you. Start sharing your screen,
Perfect.
please.
Cool. Okay. Can you see the screen?
Yeah, perfect.
Perfect. Wonderful. Yeah, hi. And first of all, thank you very much for the opportunity to speak here. I'm Janik, and I'm presenting to you today our work on active particles in moving traps. I'll focus on the first half of the title, the minimal work protocols, and I'll give a brief outlook towards the end about the information efficiency of work extraction. Before I jump in, just to say this work is in collaboration with Mike, Rosalba, and Sarah, and you may have noticed Sarah gave a talk earlier, and my talk is very much kind of an extension of Sarah's talk earlier, so hopefully that should link in perfectly if you paid attention. Beautiful. Okay, so let's jump straight in. So what is the problem? So we consider an active particle in a harmonic trap diffusing in a single dimension. And we want to move the center of the trap from one position to another position in finite time. And then we ask kind of the famous question, what is the protocol that means the time-dependent function that corresponds to the center of the trap that minimizes the average work required to move the center of the trap. To make this a little more precise, this is our model here. So we have a harmonic trap with stiffness K, which drives the gradient part of the positional, the non-flow dynamics of the particle, along with a white noise and a colored noise, which is the active force here. And we consider two different types of models for this active force. First of all, the active Ornstein-Uhlenbeck particle, which is just given by a Ornstein-Uhlenbeck particle or Ornstein-Uhlenbeck process with diffusion strength tau omega squared. And second, the round and tumble particle, which is where the active force is given by two discrete states with equal magnitude but opposite sign, which switch with a tumbling rate 1 over tau. And just to mention here, it's kind of important that we set these models up in such a way that they share a relaxation timescale tau. And the second moment or the second correlation, the correlations are matched. This makes these models comparable for what we do later. Cool. Okay, and then let's look at the work. So what is the work in this case? If we consider time-dependent center of trap, and so you move the trap, say, from a position lambda to position lambda plus d lambda, we see that the particle changes its position or its potential energy, and the change in potential energy we have to account for as work. And if you integrate this infinitesimal expression here over the duration of the protocol and average it, we get the average work of the protocol lambda. And this is the quantity that we want to minimize, which leads us to kind of the formal statement of the problem here. So we want to find a protocol that minimizes the average work given the following boundary conditions here. And in this talk, I want to present you 3 different protocols with kind of varying layers of complexity. And I'll start with the first case here, which we title the open loop case, which is the one I just set up. So what is the optimal protocol in this case? You can see the expression here. We can calculate it analytically. And just to say here, this expression is identical for the Alps and the round and tumbles. But I want to focus on the figure on the right here. So what we see is there's a linear dragging regime in the middle and discontinuous jumps at the beginning and the end of the protocol. This very much reminds us of Sarah's talk earlier, because this protocol is in fact identical to the passive case, which was studied by Schmiedel and Seifert in 2007, and Sarah discussed earlier. The same is true for the work. So the average work associated with this protocol is the same as the passive case. However, the fluctuations are increased. And in fact, the variance we can calculate here in the active case is increased compared to the passive case. Cool, that's case number 1. So what happens if we spice things up a little bit and allow for an initial measurement? So here's the setup is the same, except now we allow for an initial measurement at time t equals to 0 of the self-proportion only. And we name this measurement value V subscript 0, V0. And we kind of visualize this by this little daemon here, which can take a measurement. So the protocol in this case, we can still calculate analytically, which is kind of nice. The expression is a bit lengthy, but we see the expression here a bit simplified, is the sum of the open loop case and a correction term, which is linear in the self-proportion. The correction has some interesting consequences. It now means the protocol is non-linear in the bulk drive, and we still see some jumps at the beginning and the end. However, we see these jumps are now asymmetric compared to the open loop case, and we see interesting behavior, like for example, the initial jump in this case here is away from the target, even though the self-proportion is pushing towards the target already. And we're kind of wondering why this would be, why this is the optimal strategy. And so what we did is we looked at the cumulative work from time t equals to 0 to tf and compared the closed loop case to the open loop case. And what we find is that compared to the open loop case, the initial jump is quite costly, but it sets the system up in such a way that it allows for the extraction of work during the bulk phase, which in total reduces the amount of work required to drive this protocol. So that's kind of cool. Obviously, this is just a single example, but the main thing I want to focus on in the following is the expression of the work for this protocol. So there's 3 terms to this expression, 1 investment term and 2 extraction terms. So what's the physical intuition? The investment term basically is required to fulfill the boundary constraints of the protocol, so that we can move the protocol between A and B, the 2 positions that we want to move between. The first extraction term here is work we extract directly from the activity of the particle. And the final term here is work we extract from the potential. And I want to briefly explain how that works. So just note that a measurement of the self-proportion actually reveals information about the average initial position, which we denote here by x subscript v naught, which corresponds to an expected initial potential energy, which is in the system. And this protocol has sort of learned to extract this potential energy at the start of the drive. Cool, okay. So what happens if we now consider the work average of all measurement outcomes? And the important takeaway here is that this expression is always reduced compared to the open loop case. Yeah. So the takeaway here is kind of the initial measurement really does help to reduce the amount of work we require to drive such a protocol. And that's again summarized here on this slide. And kind of lead to the final protocol I want to present. Note that this expression here is set up in such a way that we can extract work sometimes, but not always. It's lower than the open loop case, but we may not always extract work. So the natural question sort of arises, is there a way to always extract work? And that's the final protocol I want to present to you. And the setup here is the same, except that we now relieve the boundary condition. We get rid of this second condition here and basically say we want to position a trap wherever it's energetically optimal, okay? And where is energetically optimal in this case? So the intuition is the following. We note that in a closed loop case we considered earlier, the target lambda f is in general not the same as the average particle position at the end of the protocol, which means there is some potential energy that remains unused in this protocol. And so our strategy is to basically harness this potential energy by calculating the target for which the target equals to the average particle position. And if we solve this equation here, the right side also depends on lambda f, we find the following expression here, which if we plug it into the expression for the engine, we find that this first term here, the investment term, now becomes fully 0. There's no investment term left anymore. And so this protocol always extracts work for any measurement, and obviously in this case also on average, which is kind of the summary slide we have here. So these are the 3 protocols I want to go over in this talk. And just as a brief outlook, I want to kind of tease you with how we use this to build an engine. There's some details I will brush under the rug here, like Basically, how do we drive the protocol? We need to run it repeatedly. There's some things to be said here, which I will not mention. We need to include measurement uncertainty and say some things about that, and generalize the protocols to measurement uncertainty. But if we do these steps, then we can calculate our favorite quantities for an engine, like the efficiency and power efficiency curve, which I'll again just leave here as a teaser. The only thing I want to say here is that we find run and tumble particles are more efficient than the active functional UMEC particles for the engine. And with that, I just want to say there's a lot more in the papers. If you want to have a look, please check out these references here at the bottom. And with that, I thank you and my collaborators